In this video, I'll introduce series resistors. Then we'll look at some simplifications to our circuit analysis that can result if we have resistors in series in our circuit. By definition, series elements share exactly the same current at all times. Here's a typical set of two series elements. I've defined a current I1 in this direction through this element and a current I2 in this direction through this element. If I do KCL at A, I can find out that I1 is equal to I2. So KCL at A with positive currents leaving the node is minus I1 plus I2 is equal to 0, which tells me that I1 is always equal to I2. One common way to identify series elements is if two and only two elements are connected at a node. If you're in any doubt whatsoever as to whether the two elements are in series, apply KCL to resolve the problem. Now let's narrow our focus to series combinations of resistors. These two resistors are in series. If I do KCL at this node, we see that the current through both resistors is the same. The voltage across the combination of resistors is V, and the current through both resistors is I. We followed the passive sign convention when defining V and I. Now let's define voltages V1 and V2 as the voltages across the individual resistors. Notice again that we define V1 and V2 with the passive sign convention if the current through both resistors is in this direction. What we want is an IV characteristic for this entire circuit to the right of these two terminals. So we're going to define a relationship between this voltage V and the total current I. If I do KVL around this loop, I can find that V is equal to V1 plus V2. Now if I use Ohm's law to write V1 and V2 in terms of I get V is equal to I times R1, the voltage V1, plus I times R2, which is the voltage V2. If I factor the I out, this is I times R1 plus R2. R1 plus R2 is still just a resistance. So this can be written as V is equal to I times some single resistance Req, where Req is the sum of the individual resistances. So now if I build a circuit that has a single resistor whose resistance is Req by this relationship and apply this same voltage V across these terminals, I'll get the same relationship with I. Ohm's law across this single resistor just says V is equal to I times Req, which is the same voltage current relationship as we got up here. These two circuits are the same as far as these two terminals relationships are concerned. As we just saw, this circuit on the left is identical in terms of the equations relating V and I to the circuit on the right if I set Req to the sum of these two individual resistances. These two circuits have the same IV characteristics. This means that when we analyze a circuit, we can use a single resistor to represent two resistances, which reduces the number of unknowns in the circuit. In general, we're not going to change the physical resistors in the circuit on the left with a single resistor. This is primarily an analysis technique to make the math easier. We can generalize this result for any number of series resistors. Suppose we have n resistors, all in series. Our resistors are R1, R2, up to Rn. If we do KCL at any point in this circuit, we'll see that all of these resistors share the same current. I'm going to define that as I. The voltage difference at these terminals is V, and this voltage across R1 is going to be R1 times I. This voltage is R2 times I, according to Ohm's law, up to this voltage, which is Rn times I. If I do KVL around this loop, I see that V is equal to I times R1 plus R2 plus a bunch of other resistances up to Rn. This sum of resistances can be defined as a single equivalent resistance Req. So The voltage-current relationship across these terminals is the same as for a single resistor if Req is the sum of the individual resistances. One common application of this is to reverse the process in order to create a desired resistance from multiple resistors. For example, when we design a circuit, we may find that we need a resistance that isn't readily available. In order to create a prototype of our design, it may be easier to use available resistors to create the desired equivalent resistance. For example, say we want a resistance of 9 kiloohms, but we don't have a 9 kiloohm resistor available. Our series resistance formula says that we can use several resistors whose resistances sum to the desired value. So if we have access to 2.2 kiloohm resistors and 6.8 kiloohm resistors, we can create our desired resistance by putting these resistors in series. Let's use an ohm meter to check this out. Here's my 2.2 kiloohm resistor. This is a 6.8 kiloohm resistor. I'm using a DMM to measure the resistance across the series combination, which is 9 kiloohms.
Circuits, Chapter 2, Part 2, Talking Head 8, Take 2, and action.
Combining resistances in series can be useful in both circuit design and analysis. Another common use for series resistors is to create what's called voltage dividers. This is the topic of our next video.